All right, welcome everybody. Today I want to talk about lateral movement at level 1. And that's because there's quite a few devices at level 1 that sit at the intersection of different mixed networks. They might be connected to an RF modem, which talks to a wireless HART network, or to a Tetra network, where you can have SCADA communications, or there might be Fieldbus networks nested behind this device, and even connections to third-party packaged units maintained by external parties. And while there has been some research in the past on upstream hacking from level 1, for example, from an RTU all the way up to a SCADA, there has been very little attention to arbitrary east-west movement at this level, as well as deep downstream movement. So a question you might ask is, why bother with this? This is all stuff that's very deep down in the soft underbelly of OT. Why care about this? Well, because I might want to cross certain security perimeters that do exist at these levels. After all, if a device is multi-homed between different zones with different security profiles, it is a perimeter device, and it should be hardened accordingly, in the same way that you would harden a workstation that sits between different security segments. One example of this is something you can find in the interaction between the basic process control system and safety instrumented system architectures. Obviously, this can be generalized to any set of distinct but interacting control systems, but we take the BPCS SIS interfacing as an example. On the left of the slide, you can see an increasingly common architecture where the BPCS and the SIS basically interact at a level above level 1, and this segmentation is typically done through regular firewalling. But another architecture you sometimes encounter is the so-called interfaced architecture, where the controller in the BPCS has a direct point-to-point link to the safety controller. And this can be a serial link, this can be an Ethernet link, but what matters is that it is a very restricted point-to-point link. Now, why would an attacker want to cross into these safety systems? There's many obvious reasons for this, but one of the reasons are so-called SIS bypasses. And for the people unfamiliar with this concept, there's various good reasons why you might want to bypass safety functions. For example, as part of process startup, as part of process transitions, or regular scheduled maintenance. And as you can see illustrated in the simplified block on the slide, a bypass allows you to bypass a single actuator, a sensor, or entire safety instrumented function within the SIS. But before you can activate a bypass, it needs to be explicitly enabled. Now, historically, all of this stuff used to be hardwired, but increasingly activation of bypasses is done through software signals, including software signals sent from the BPCS to the SIS. However, what you sometimes see is that the enabling of a specific bypass will require a hardware switch to be turned, and this hardware switch might not be hooked up or reachable from the BPCS at all, and will require you to have a sort of foothold within the SIS. In addition, these bypasses might have certain constraints. They might have timeouts on how long they are active, and there might be limits on the numbers of simultaneously active bypasses that an attacker might want to disable. So these are all reasons why you might want to move very deeply into the SIS. Another aspect of perimeters that exist at level 1 are through so-called Fieldbus Couplers. And so for those unfamiliar with the concept, a Fieldbus Coupler is essentially a sort of limited gateway that sits between different Fieldbus networks that might hook up a Profibus DP network to a Profinet network. And essentially what it does is it moves a limited set of I/O values between different masters on these buses. Now, this is not necessarily a perimeter, but what you see quite frequently is that when you're dealing with packaged units, for example, HVAC, or for example, an entire gas turbine, some asset owners opt to put a Fieldbus coupler in between that packaged unit, where a vendor might have remote maintenance access, and their own basic process control system. And because essentially only a few I/O values are moved up and down, and these devices used to be historically dumb, there used to be a reduced attack surface. And these kind of couplers are seen as sufficient perimeter by themselves. But as these devices have gotten smart with all the stuff that entails, that is typically no longer the case. The second reason why you might want to bother with lateral movement at level 1 is because you need a certain sort of granular control over these systems. If you look, for example, at this slide, you have an attacker, and he's able to reach out to the top-level master PLC. And behind that PLC, there are different nested networks of other PLCs and field devices And they expose their own set points, process variables, configuration interfaces to this PLC, but obviously not all of that is exposed at the level of the master PLC. So if I want to manipulate what is going on in that system, I cannot immediately influence what is lying behind that master PLC. Now, in some cases, traffic might be routable over SIP or S7 to these PLCs, but in other cases, there might be non-routable links behind it. And even if the traffic is routable, that means that I often cannot send malformed packets over those routable links, and I can also not reach out all the interfaces that might otherwise be exposed. So that means that I might need to initially get code execution on this master PLC before I can move to those other PLCs in order to bypass any sort of functional or safety limits within them. Now, this kind of thinking is very common in automotive exploitation. What you see a lot there is that attackers, they initially get code execution on some sort of a multimedia unit, but it doesn't grant you deep access to the CAN bus you need access to. So initially, they first will need to bypass some sort of a CAN command filter that exists within the CAN controller, and then they will need to pivot to a gateway in order to access the exact kind of CAN bus to achieve the kind of effects they want. So that's essentially what we're trying to do here as well for OT networks. So what do vendors and standards say about this kind of lateral movement and these kind of connections? So it seems that over the past years, there has been a general acceptance of the integrated, interfaced, and common architecture for BPCS and sys integration that comes with the typical segmentation advice. However, there does seem to be quite a few pieces of guidance out there that say that non-routable or serial point-to-point links are sufficiently segmented of themselves. And that is something that is definitely not true in my opinion. Not all the guidance says this, but there's some guidance out there. And to illustrate this a little bit in more depth, we built a little proof of concept scenario to showcase how this looks like in practice. So we based our scenario on the scenario of movable bridges. So as you can see on the slide, you have a bascule bridge, and the bascule bridge leaf opens as the counterweight moves into the pit. And as the leaf closes, it will hit a limit switch that essentially says you're about to close, decelerate to creep speed so you don't hit the bearings too hard. And once it's fully closed, it will allow the lock bar to unlock and then essentially close and put the leaf in a sturdy place. Now, there's many ways in which an attacker can seek to attack a bridge structure like this, but one scenario, obviously, is attempting to close the bridge leaf at full speed and hit the bearings, possibly with the lock bar driven. Now, this is not something you can do from the SCADA interface. You will need to bypass a lot of functionality for this. You will need to make sure that the deceleration to creep speed doesn't happen. You will need to bypass the leave and the lock limit switches. And the second scenario has similar constraints. So, for example, if we want to close at maximum velocity and then trigger an emergency stop, which is not graceful and will cause the inertia of the counterweight to have large forces move throughout the bridge leaf, we will need to bypass creep speed as well as have an ability to trigger this emergency stop from our position point as an attacker. Now, we sketched out this little architecture to come with these scenarios. It's based on several real-world bridge management systems that we saw. And what you essentially have here is that each of the individual bridges are delivered as packaged units managed by a local municipality, for example, while the overall bridge management system is maintained by a regional or a central government agency. Now, what happens is that from the SCADA interface, they talk to a coupler device, and this has a very limited interface that doesn't allow you to talk to the bridges directly. You just are able to manipulate some values that are exposed on part of this coupler that say open or close this particular bridge. And the coupler then talks to the individual bridges. And each of these individual bridges is controlled by an object PLC that exposes, again, a limited set of values. For example, something that allows you to initiate an opening or a closing sequence, but definitely nothing granular that allows you to bypass this creep speed or manipulate these limit switches. So an attacker who wishes to achieve a scenario like we just sketched will first need to get code execution on the coupler, and then from there hop onto the object PLC, and from the object PLC maybe manipulate these detailed bridge systems over the Fieldbus, in this case a CANopen Fieldbus we picked for this scenario. And if they want to bypass any sort of safety constraints, they will need to hop across the restricted point-to-point link to the safety controller and achieve their effects there. So in our scenario, we used as a coupler device, we used the Wago 750 series, but really could be any sort of coupler. And this talks to the object PLC controlling the bridge, which is a Schneider Electric M340. We can't talk directly to the M340, so first we want to be able to bypass that sort of limit by hopping onto the Wago. And the way we do this is we exploit a malformed FTP packet, so we get code execution, pre-authentication, by exploiting one of the Nucleus 13 vulnerabilities that we covered a couple of years ago in our research. Once we have code execution on the Wago coupler, what we do is we hook its Modbus handler to effectively become a proxy handler that allows me to speak the UMAS protocol, which is a protocol proprietary to Schneider Electric under function code 0x5A to the M340 PLC. Oh, it's one too far. So yeah, once I can talk to the object PLC, I can speak this Schneider UMAS protocol. This is one of the best understood and reverse engineered proprietary protocols out there. Historically, it used to be unauthenticated, but Schneider introduced an application password at a certain point to restrict the ability to start and stop the PLC and download the logic and all that sort of stuff. A vulnerability was discovered in this by multiple independent parties because of the way it works as outlined in this slide. So the first thing you effectively do is you read a memory block that holds a hash over the salt and the password. Then you do a nonce exchange with the PLC. Then you do a take reservation request where you use this secret and the nonces. And then you send authenticated messages essentially to this PLC with these nonces. Now, obviously, if I can read this memory block with the secret, then essentially it's client-based authentication. So Schneider fixed this. This secret is no longer in the memory block, but there were a few other ways to bypass this authentication that we did not see covered before and which we reported to Schneider in the advisories that you can see on the bottom of the slide. So one of them is the ability to do a reservation replay. What I can do as an attacker is I can sniff a legitimate authentication hash, and then I can replay that because the nonces are globals held by the PLC in memory. They're not tied to any specific session or any specific IP, and they don't refresh automatically. So if someone legitimately authenticates to the PLC, and I sniff that particular authentication hash, and I don't do my own nonce exchange, those old nonces will still be valid, and I can use those as part of my replayed authentication hash. A little bit of a more convenient way to bypass this for an attacker is to forge authenticated requests. I can sniff nonces and the reservation ID, and because essentially these reservation IDs are not tied to any particular IP or session, and because, as you can see in the previous slide on the bottom, there's no actual secret in the authenticated request, as long as I know the nonces, I can just forge arbitrary requests and inject them in that section. So once I'm able to bypass the authentication, I want to get code execution on the M340 PLC. Now, there's different approaches in prior work. Some of them include downloading logic to the PLC, for example, vulnerable messages as part of UMAS, which have been exploited, vulnerable TCP IP stacks on some of the Modicon family PLCs. But what we wanted was an approach that works on a fully updated PLC and that allows for hot patching. So we don't want the logic to restart, which might cause process upsets or alarms to go off. We don't want any of that disruption that comes with the logic download. We also wanted to be a little bit hostile to forensics, so no project checksums that change and so on, and use an obscure protocol feature that evades most IDS. And before we can delve into how we did that, you need a little bit of background about the Modicon internal organization. So the Modicon family of PLCs uses something called the application binary file format, the APX format. And that format is a part of its project files, and that essentially organizes the PLC memory into different areas. And each of these areas is organized into different sections, and each of these sections holds a bunch of blocks. And these can be data blocks, these can be code blocks, these can be source blocks, whatever. And each of these blocks is linked to an entry in the relocation table. We have an RTE number that basically describes this is where the block is located, and these are its attributes and permissions and so on. And this is what the PLC essentially loads and how it organizes all of the project in its memory. So what we found is that there is a previously unexplored subfunction within UMAS called the CSA request with function code 0x50 that allows you to make these virtual pages on the PLC. And you can read and write to them and schedule them for execution. And you can fill these pages up with a proprietary command set that allows you to read, write, and copy, and so on from these different blocks. So you can directly manipulate these blocks as they reside in memory. And this is, from an attacker point of view, very interesting because it happens live. I don't need to restart the logic. I don't change these typical forensic indicators like the project checksum, and any modifications to executable blocks don't show up in the source code when I upload the project again to my EWS. Now, initially, it seemed a little bit hard to exploit because you can't write directly to these code blocks. But we found another issue which we reported to Schneider, and that essentially meant that we could write to a data block and then copy from that data block to an executable block because that copy operation did not have the permission check that the write operation did have. So what we then can do is we can essentially copy to that code block, and when it executes as part of the regular logic, our malicious payload will execute. And what we did with that is essentially this. Our code is executed as part of the regular scan cycle, but we want to get out of the runtime executive because we have to deal with watchdogs and all kinds of restrictions. So we initially inject a stager payload, and that stager payload allows us to move to a different area of the M340 firmware where we have arbitrary access to talking to the backplane device driver, the CANopen device driver, the VxWorks socket library, and so on. And that allows us to have this detailed manipulation of the field devices that are connected to its CANopen bus that otherwise would not have been possible. So we can now talk to the M340 CANopen API and use these standard functions that are part of CAN in automation, where you have different service data objects that allow you to get code execution on the field devices themselves. For example, through in-band code downloads that allow you to download application logic or firmware to these field devices, or in some cases just have arbitrary read and writes to the memory of these field devices to debugger functionality that's exposed through a different SDO. And we looked through various CANopen device manuals and found that if there was any authentication for this at all, what typically happened is that you just had a 32-bit value that was written to a different SDO, and that was typically a static value, so to prevent engineering errors rather than security. Now, the second objective after we have code execution on the M340 was to essentially move through the safety system. Now, in our case, in our little demo, we had a Allen Bradley guard logics as the safety PLC, and that had an Ethernet module that was hooked up to the M340 over a non-routable point-to-point link. So we can't just send SIP messages to it, we can't just download logic, we have a very restricted interface here. So in order to be able to cross this little bridge, what we do is we use the VxWorks raw sockets API to send malformed IP options to this Ethernet module in order to exploit one of the Urgent 11 pre-authentication remote code execution vulnerabilities on the Ethernet module. Now, on this Ethernet module, you have no need for further privilege escalation because you're already running in supervisor mode and there's no task separation there. Now, once I am on the Ethernet module, I'm no longer bothered by the restrictions of this point-to-point link and everything that's there, because I can talk directly to the backplane device driver of this Ethernet module that allows me to talk to an ASIC, which is called the Apex 2 ASIC, which is the backplane ASIC for the Logix backplane bus. And this is essentially a SIP-based bus. So now I can send arbitrary SIP messages to the remote IOs, to the CPU module, and manipulate any of these tags that might be related to the safety bypasses. So to illustrate this a little bit more, I have a little video that should start playing.
How to move laterally through OT systems at level 1 in order to gain deep access to nested control systems and cross-restricted perimeters between different security zones. The demo setup shown consists of a Wago 750 Ethernet coupler offering a limited gateway interface to a nested Schneider M340 PLC. The M340 PLC is in turn connected to an Allen Bradley guard logic safety PLC via a restricted point-to-point link to its Ethernet module. None of these PLCs are conventionally reachable from the attacker's initial point of access. The attacker starts by exploiting a Nucleus 13 vulnerability for remote code execution on the Wago coupler gateway. Once the implant is in place, the attacker can move beyond the coupler's restricted interface into the nested networks behind it. In order to reach the nested Schneider M340 PLC, the attacker will instruct the implant to forward their Schneider UMAS traffic. In addition, the attacker will instruct the implant to sniff Schneider UMAS authentication traffic. Meanwhile, an unsuspecting engineer authenticates to the M340 PLC as part of regular operations. Having sniffed the engineer's nonces, the attacker will now reuse them to send forged but seemingly authenticated UMAS traffic to the nested M340 PLC. The attacker now forges requests containing the undocumented CSA commands in order to gain code execution on the PLC itself without disrupting its logic. Meanwhile, the engineering workstation cannot tell that anything's changed, as the software shows everything's still okay, granting the attacker a high degree of stealth. Once their implant resides on the M340 PLC, the attacker can now launch additional exploits on previously unreachable interfaces, such as the restricted point-to-point link between the M340 PLC and the GuardLogic Safety PLC. In order to gain full control over this safety PLC, the attacker launches one of the Urgent 11 exploits from its implant on the M340 PLC. Once the attacker has code execution on the Safety PLC Ethernet module, they can talk directly to device drivers offering access to the PLC backplane and module peripherals as shown by manipulating the module's display in wider controller LEDs. Similarly, the attacker's unconstrained access to the M340 PLC's internals, as shown by manipulating the CPU module's LEDs, allows them granular access to local and remote field devices connected to the CAN bus or backplane, demonstrating how lateral movement at level 1 grants attackers deep access to complex control systems.
All right, so a little bit about disclosure. We coordinated the disclosure of this with Schneider Electric, reported these issues in April and July of last year. Advisories were recently released. There are mitigations for now, but remediation plans are forthcoming. We suggested a retrofittable authentication fix by using the secure remote password protocol together with HMAX to essentially tie these authenticated messages to the initial mutual authentication session. So that is something that could be retrofitted on the protocol, luckily. In conclusion, there's likely a lot of network crawl space that's not on your radar. Like at the level 1, there might still be perimeters that you haven't looked into to external systems and even systems that are, remotely maintainable. So look into that. If a level 1 device sits between different segments, it needs a perimeter security profile. Stop treating certain links, like serial links, point-to-point links, non-routable links, as if they're immune to all of these issues, because they're not. The impact of a compromise is not limited to the explicit capabilities of that link or just its first-order connectivity. Just because I have a vulnerability in an Ethernet module doesn't mean the impact is limited to communications. I might use that as a stager to get, for example, to the actual CPU. And with deep access, things become possible which change potential impact. So you might have been relying on functional and safety limits within the field devices that could be bypassed through an attacker taking this sort of route. There's a full report with way more detail than I could go into, including some mitigation and detection and forensics advice. I urge you to check that out, and if there's any questions, I take them now, so move up to the microphone.
Question, the problem you're talking about now with attacks coming from L1, would you say it would be even worse if it's not wired? If it's wireless, that you actually expose your L1, L2 stuff over wireless?
Yeah, definitely. I've seen some environments where, for example, you have wide area SCADA networks over something like Tetra or DMR, and there you have your communications for level 1 all in the open. I mean, obviously you have way other issues if that is your case, but yeah, that makes it a lot easier to get already to level 1, obviously, if you can just jump on there.
I had a question about the monitoring piece. I know you had mentioned that that's in the report, and I know that there's only a couple minutes, but I was wondering if you could give any sort of TLDR on the monitoring strategy for something like that?
Very briefly, in the case of this specific attack chain, being able to spot these write messages that are part of UMAS, as well as certain things like, for example, watchdog failures on top of the PLC. If the attacker's not careful, you're going to trip up the watchdog with this, and you can monitor that. And in case of, for example, the Allen Bradley guard logics, you have a web page that shows you what tasks are being run by VxWorks. So you could put a monitor there that says, you know, did someone spawn a malicious task? What resources are being consumed? And we mentioned some of that kind of stuff in the report.
So is that monitoring capability something we could do with iInspect?
Yeah, so for example, these attacks and the protocol level attacks, that's definitely something that iInspect is able to do.
Excellent, thank you.
My question is kind of similar to his about detections. And so one of the top 20 secure PLC coding practices is monitoring the scan cycle time. Could you comment on how this kind of attack would potentially affect scan cycle time?
So initially, if you look at what we did with the M340, that'll have some impact on scan cycle time because for a little bit you're in that particular task. But once you break out and you schedule a new RTOS task for your malicious code, then I don't think it affects that as much anymore. So it's for a little bit. But there's other resources you can monitor on the side.
Yeah, thanks so much.
Hi, I'd like to know, is it possible to implement something like a SMB signing in this environment that would have the ability to block that replay attack that you did to get the authentication?
Yeah, I mean, it's always hard to retrofit, security on protocols that were originally insecure by design. And, even though this is broken, at least the Modicon family took the attempt to put authentication on there, which a lot of level 1 devices still have to do, so that's good. And one of the suggestions we describe in the report is to use the secure remote password protocol for initial mutual authentication, derive a key from that, and then use an HMAC to sign all of these messages and tie that to the initial mutual authentication. And you could, in my opinion, retrofit that on the UMAS protocol, but whether that's going to happen or not, that's not up to me. But I think there's possibilities there, yeah.
Okay, thank you.
All right, thank you.